Today we're talking about Karl Friston's free energy principle, and it's a guide to your brain's balancing act. When scientists talk about attention, they don't just mean staying focused on a task. In modern neuroscience, attention is defined in terms of how your brain decides which information to process more precisely and which to treat as less reliable. It's about managing uncertainty in a world that constantly bombards us with sensory data. Hey everyone, I'm Henry and you're watching day 73 on my channel, Henry's Millions, where I dive deep into psychology and neuroscience, helping you explore and master the forces that shape your life. So today's talk is based on a 23-page research paper by Feldman and Friston titled Attention, Uncertainty, and Free Energy, published in 2010 in the Frontiers in Human Neuroscience. I went through it, so I did it for you so you don't have to, and put together a nice, easy, conceptual talk for us today. So get your coffee and let's go. Uncertainty here has a precise meaning. It refers to how confident your brain is about what's generating the sensations it receives. Our senses continuously capture signals, patterns of light, vibrations in air, chemical traces, and your brain tries to infer their underlying causes. What object is reflecting this light? What is making that sound? Each of these inferences come with a degree of confidence. If the input is clear and consistent, uncertainty is low, and precision, which is the inverse of uncertainty, is high. So if the input is ambiguous, uncertainty is high and precision is low. So this way of thinking treats perception as a kind of probabilistic inference, similar to what's done in statistics or machine learning or some forms of gambling. Your brain doesn't just record reality. It constantly generates hypotheses about what's out there and updates them based on incoming evidence. So attention in this formula is the process of estimating and adjusting the precision of prediction errors. Those are the differences between what your brain expects and what actually arrives through the senses. So only the most precise, high-value prediction errors are allowed to strongly influence what we consciously perceive. So this brings us to the deeper puzzle. This allocation of precision is not random or isolated. It is part of a much broader principle known as the free energy principle. It's a unifying theory for how we resist disorder and remain in viable states. Free energy can be written as complexity minus accuracy. Minimizing it guides your brain towards models of the world that are detailed enough to explain sensory data, yet simple enough to avoid wasteful overcomplication. And by the end, we will see why improvements in accuracy almost always come at the price of increasing complexity, and how attention is one of your brain's key tools for managing this trade-off. So let's talk about attention as precision control. So when neuroscientists speak of attention, they are moving away from the idea of a simple spotlight or filter that selects some information while ignoring the rest. Instead, attention is now the way the brain estimates precision, how reliable a stream of information is, so that it could decide where to invest cognitive effort. In technical terms, uncertainty refers to the width or variance of a probability distribution that represents possible causes of sensory input. So precision is the inverse of uncertainty. When the mind is highly certain about the source and meaning of a signal, precision is high. When it's unsure, precision is low. So let's break this down. Every moment, your brain is flooded by sensations from all around you. Light, sound, touch, and countless internal signals. To make sense of this, your brain uses an internal model, it's called a generative model, that generates hypotheses about what's causing these sensations. Perception, therefore, is inference. The mind constantly guesses what's behind each sensory signal. Remember, your mind is encapsulated in a skull. It uses senses to to get the sensory input, so it has to make predictions and guesses about the outside world. So inference itself is probabilistic. There is always some uncertainty, and your brain must assess how much weight or precision to assign the new evidence. And attention is about modulating that weight. So the way this works inside the brain, according to the free energy framework, is through hierarchical inference. Think of your brain as a multi-layered prediction machine. Lower layers process raw sensory data, while higher layers make more abstract predictions. If a lower layer finds a mismatch between the prediction and the actual input, a prediction error, it passes that error up the hierarchy. But not all errors are treated equally. Their influence is weighted by their estimated precision. Only high precision, highly informative errors get prioritized, and that shapes our perception and subsequent action. So attention corresponds to dynamic changes. We're talking a little bit deep into neurobiology right now, just to get your feet wet. Attention corresponds to dynamic changes in synaptic gain. It's the responsiveness of neurons reporting prediction errors. And these mechanisms directly encode precision. Upregulating the gain strength strengthens the impact of precise, reliable prediction errors, while downregulating it mutes ambiguous or noisy signals. So by viewing attention as precision control, we see why it's integral to optimizing inference under uncertainty. Rather than simply filtering information, attention helps the brain decide in real time which signals most deserve to drive updates in our beliefs and behavior. And every act of focusing, whether on a sound, a word, or a thought, reflects the brain's best guess about where high-value information lies, given the current context. So let's talk about competition and context here. Attention, as you know, is not an unlimited resource. Whenever multiple sensations or signals arrive simultaneously, your brain faces a problem. Which ones should influence perception most? So this challenge is addressed by what scientists call competition for representation. In a crowded environment, whether it's a busy street, a full inbox, or a cluttered visual scene, stimuli must compete for access to limited cognitive processing. And the concept of biased competition captures this process. Inputs vie for neural resources, and certain contextual factors can bias the competition, so some signals win out over others. So to see how this works in practice, consider something called, it's a classic Posner cueing paradigm from experimental psychology. I'll explain it to you. Subjects are instructed to stare at a fixed point, and before a target appears, a cue, like an arrow, tells them to expect the target at a certain location. Remember, they're looking at a fixed point. When the cue is correct, a valid cue, responses are faster. But if it's wrong, an invalid cue, reactions are slower. So this demonstrates that attention can be shifted not just by what appears, but by the brain's expectation set by the cue about where valuable information will be. So this shift happens even without any eye movement of the eyes. You can try this yourself at home. You could focus on one thing, and then practice giving selective attention to other things in your field of vision. So the brain reallocates its precision budget toward expected locations. Now, Feldman and Friston showed that these effects emerge naturally from precision estimation. Your brain doesn't need a special spotlight process. It allocates precision or confidence in a way that amplifies expected signals. When the cue is valid, precision is shifted to that location. So prediction errors from that site have amplified influence. And when the cue is invalid, prediction errors from the target site from the target start out with low precision, so it takes longer for your brain to accumulate enough confidence to react, resulting in slower responses. So this approach also explains biased competition. When multiple targets appear, one in a queued location and another in an unqueued location, they compete for precision. The predicted relevant queued stimulus is given more precision and more influence over further perception and action. So competition is resolved not by suppressing all the others, but by dynamically weighting signals according to their expected reliability. So these operations, both prioritization and resolution of competition, they're not special tricks layered on top of perception. They emerge from optimal inference itself in a probabilistic, uncertain world. This process is dynamic and constant and context sensitive. As expectations in the sensory landscape change, so does your brain's estimation of which inputs deserve high precision and therefore your attention. So whenever you attend selectively, something stands out to you. Your brain is implicitly solving a competition, using context and expectation to distribute precision, essentially betting on which data are most likely to matter. So real briefly, let's do a quick refresher on predictive coding, linking attention to perception. So to understand how precision of your attention operates within perception, we need to explore predictive coding. It's a fundamental mechanism in modern brain science. The basic idea is that your brain continuously generates predictions about incoming sensory data based on its internal model of the world. These models aren't simply static beliefs. They are a hierarchy, organized set of expectations about patterns, objects, events, and their causes. When new sensory input arrives, lower levels in the cortex compare what's actually sensed against what was expected. The difference between the incoming data and the predicted data is called a prediction error. This error isn't just noise or mistake, it's valuable information. It tells your brain exactly where it's missing something or making incorrect assumptions. The key, according to Feldman and Friston, is that not every prediction error has the same impact. Errors are weighted by their precision, and that's the confidence that the brain assigns to each discrepancy. So highly precise errors are emphasized and drive rapid updates. Low precision errors are mostly ignored. So notice how attention fits into this process. Attention is the process by which your brain modulates the precision of prediction errors. When you attend to a particular feature, event, or location, your brain is amplifying the error signals coming from that source. This means your internal model listens more closely to highly reliable or important incoming evidence. Now, the estimation of precision isn't fixed. It dynamically adjusts based on context, expectations, and past experience. So to clarify, this type of attention doesn't operate as a separate spotlight or mental filter, but as part of a Bayesian inference scheme embedded in the biological architecture. And contextual cues, whether bottom-up like a loud sound or top-down like you're expecting an email, set hidden states in your brain that determine which prediction errors receive what level of gain or amplification. So what you perceive and what you react to are determined by this ongoing process of model comparison, prediction, and error correction. So by dynamically controlling the influence of prediction errors through estimated precision, the brain achieves a balancing act. It can rapidly respond to surprising and important changes in the environment, when errors are precise and informative, while avoiding constant overreaction to irrelevant noise when errors are too uncertain to matter. And the emerging architecture underpins both the fluid adaptability of precision and the selectivity of attention. So as you will see, predictive coding and precision controlled together set the stage for the free energy principle. The idea that your brain minimizes this global quantity called free energy by achieving the best compromise between explanatory accuracy and model complexity. The principle, free energy, formalizes how living systems continually fine-tune what they pay attention to and how precisely they process what matters most. Okay, now for the free energy principle and why it's complexity minus accuracy. It's really a fascinating discovery. The concepts of attention, uncertainty, and predictive coding converge on a deeper organization of brain function. It's the minimization of free energy. Free energy provides it's a mathematical framework for how biological systems, like our brains, resist disorder and maintain stable, adaptive models of their environment. Now, free energy represents a bound on surprise for an internal model. Your brain constantly receives sensory signals and tries to explain them. Essentially, it's a set of beliefs about what causes those sensations. The better the model fits reality, the less surprising the incoming data are, and the lower the free energy. But there is a cost. Making a model highly accurate often means making it more complex. Now, mathematically, Feldman and Friston's paper expresses free energy as complexity minus accuracy. Let's break this down a little bit. Accuracy measures how well the model predicts sensory data, how closely your brain's hypothesis matches the world, low prediction error. And complexity quantifies how much the current beliefs have shifted away from their priors or initial expectations. It's a formal measure of surprise. So why does increasing accuracy tend to increase complexity? Because accounting for more details in the world and reducing prediction errors requires the brain to adjust its parameters away from their simple prior settings, constructing a richer, more nuanced model. And this process incurs a complexity cost. The brain must compute, store, and maintain more information, which is energetically and structurally demanding. So the insight from Feldman and Friston is that minimizing free energy requires balancing these two forces. If the brain focused solely on accuracy, it could easily end up with overfitting hyper-complex model, one that perfectly explains every observed detail, but is inefficient, inflexible, and costly. On the other hand, prioritizing simplicity, low complexity, risks a model that's too coarse, missing key patterns and causing persistent prediction errors. So optimal behavior emerges from minimizing free energy, making the model as simple as it can be while still being accurate enough to account for the sensory evidence. So this is, so to speak, the sweet spot of inference and attention. Just enough detail to explain reality, but not so much complexity that the system becomes overloaded. Now, attention plays a direct role in this balancing act through precision allocation. By directing precision to prediction errors that matter the most, those that are highly informative in a given context, the brain increases accuracy where it's needed, but limits complexity elsewhere. So this dynamic approach ensures resources are used efficiently, avoiding unnecessary elaboration of sensory input that isn't relevant. And the free energy principle offers a unifying explanation for why cognitive effort, learning, and focus all have real trade-offs. When we strive for greater clarity or pursue new understanding, whether in science or skill building or day-to-day adaptation, our brains are not just passively absorbing information, they're actively tuning their models, balancing the energetic costs of complexity against the benefits of increased accuracy. All right, what are the implications for understanding ourselves? The theory outlined in Feldman and Friston's work offers important perspectives for everyday life, personal development, and mental optimization. I had to make it applicable to you. We have to find a way to apply it. So at the heart of this framework is the idea that free energy minimization, the process where our brains balance complexity and accuracy, has deep consequences for how we experience effort, distraction, focus, and learning. First, consider the implications for mental effort and cognitive fatigue. When we strive for greater understanding, our brains work to expand the internal model to accommodate new, more accurate information. This increase in accuracy carries an increase in complexity as the model becomes richer and more demanding. In mental effort, the sense of working hard can be understood as the energetic and structural cost of updating our internal models. So whenever you learn a new skill or adapt to new circumstances, you're paying the complexity cost for this improved accuracy. So this relationship helps explain why intellectual work can be taxing and why sometimes simplifying our approach can provide relief. So managing distraction can also be reframed in terms of optimizing free energy. In a world of constant information overload, endless updates, notifications, our brains are repeatedly challenged to update models with each incoming accurate update. This can drive up complexity until the resources for further processing are saturated. So the principle suggests caution against chasing every possible update for the sake of accuracy, as overloading the model can lead to confusion and mental fatigue. Instead, selectively attending to precision-worthy updates preserves the optimal complexity-accuracy balance and supports sustainable cognitive function. So during skill learning and mastery, the theory provides a valuable organizing idea. Whether practicing an instrument, mastering a scientific field, or improving at a sport, pushing for greater expertise means pursuing lower prediction error, more accuracy. And according to the free energy principle, this process will naturally expand and complicate the internal model. Expertise comes at a cost of energy and structure. However, the brain intuitively regulates this process, often limiting further investment if costs outweigh the perceived benefits. So this framework encourages deliberate investment of attention. Being mindful of where and how much precision is allocated protects you against unnecessary complexity. And effective focus means consciously choosing when it's worthwhile to pay the price of a more complicated model, whether by tackling a difficult new concept, upgrading your belief, or reviewing complex information. So the brain does this balancing act. It's amazing. So bringing these ideas together, thanks to Friston and Feldman, formulation recasts attention, perception, and learning as aspects of a single principle, the minimization of free energy, expressed as the balance between complexity and accuracy. You should know this well by now. As we've discussed, attention is not just a mental spotlight, but a computational process of allocating precision, selectively amplifying the most reliable prediction errors to optimize inference in a world full of uncertainty. So the mechanism driving this optimization is predictive coding. I have more than one video about predictive coding starting from day 60. If you're interested, go check those out after this video. Predictive coding is where higher order cortical areas send predictions to lower areas. Discrepancies are flagged as prediction errors, weighted for their precision. By modulating these weights, attention controls how strongly errors update the internal model, ensuring that only those with the highest informative value are allowed to drive change. So the free energy principle formalizes the trade-off at the heart of cognition. The pursuit of increased accuracy in our internal models almost always demands a rise in complexity. The best models are not those that explain every detail, but those that strike a sustainable balance. Cognitive effort, learning, and adaptation are expressions of this balancing act. So for everyday life and personal growth, we should deliberate about where and when to deepen our models versus when to simplify and conserve resources. The drive for more knowledge, skills, or clarity must be matched with an awareness of the cost, whether it's mental fatigue, confusion, or overload. And ultimately, the brain's balancing act is not just a theoretical construct, but a key to thriving under uncertainty. By minimizing free energy, we manage perception, learning, and well-being, not by chasing perfect accuracy, but by remaining flexible and efficient. That concludes our talk for today. I hope you enjoyed it. Please take a moment to like and subscribe to Henry's Millions. It motivates me to keep making these videos for you. And thanks to Karl Friston, and thank you for watching.